Right. Now we will start our lecture, lecture number 4. And we will start, hello everybody, and we will start with a theorem. We had no time to complete this theorem, to prove this theorem, but we will need this theorem and this proof in what follows, and so I will start with the theorem about so global existence of a solution of an initial value problem. Okay, I'd like to recall that we consider the differential equation in the vector form. This is the vector function. The first derivative is equal to f of t x of t. X is a vector, f is a vector function. This is our differential equation. And we consider an initial value problem. X of t0 equals x0. Okay, and if the function f is good enough, so if it is continuous and locally Lipschitz, then the Picard-Lindelof theorem guarantees that this initial value problem has a solution locally in the neighborhood of the point t0, x0, and this solution is unique. Well, and on the preceding lecture, we interested in the global existence, the problem of global existence, because the Picard-Lindelof theorem is a local theorem, but we want to know the maximal interval, and we spoke about maximal interval of the solution. So Picard-Lindelof theorem guarantees that there exists a neighborhood. In some neighborhood of this point, locally the solution exists and is unique. But we want to know the maximal interval, and we want to study the problem of global existence of a solution. So we have defined the maximal interval of the solution. So this is the so we can't extend the solution out of this interval, out of this maximal interval. So this is a maximal interval. But we want to study and to prove the following theorem. I will call it global existence. So if D is a direct product of some interval I, so I is an interval AB in R times Rn, if D is this domain, and if the vector function f of tx is defined in D, and it is continuous and locally Lipschitz in D. Just a moment, I will have a look. The pronunciation, spelling, Lipschitz in D. And satisfies, so locally Lipschitz. And in addition, suppose f satisfies the following inequality. So the norm of f of tx doesn't exceed the product a of t is some function in I times the norm of x plus b of t, where a of t and b of t are continuous and non-negative functions in the interval I. And locally Lipschitz, so continuous and non-negative. So if and so on is not good, I think. Let D be right. So I don't know. So this phrase is too long, I think, too complicated, right? If this. So the first part, D is this, I times Rn, F is continuous and locally Lipschitz. The first condition, the second condition, then the so inequality. So then the solution. So for any t0 from I and x0 from Rn, the solution can be extended to the entire interval I. So the initial value problem has a unique solution in I. For any, so the initial value problem. I will use this abbreviation. So initial value problem. This initial value problem has a unique solution. In I, in entire I. So it can be extended to the entire interval. So if D is this, then the maximal interval is I. So this is the theorem states something about the maximal interval. Maximal interval is I. So the solution can be extended on the entire interval I. So I will prove this. So we will use the theorem about the leaving any compact set. So it was stated, this theorem was stated during the preceding lecture. Well, and we will use this theorem. Okay, so take any t0 from I and x0 from Rn. We will consider a solution and suppose J is a maximal interval. Of x. Okay, let it be from alpha to beta. And it is a subset of I, of course, because we are inside D, right? So our function is defined only in the direct product of I and Rn. So this is our domain, and we do not consider the domain outside D, so the regions outside D. So we are inside I. Alpha, the interval from alpha to beta is the maximal interval of this solution, and it is inside I. And we want to prove I coincide with J, but suppose the contrary. So assume that on the contrary, J is a proper subset of I. So this means that alpha or beta is inside I is okay, I is AB. This means that alpha is inside AB or beta is inside this interval. So if, on the contrary, J is not the same as I, so it can be this proper subset of I. And this means that alpha is a point in AB or beta is a point AB, and so both cases can be considered similarly, so without lots of generality, we will consider this case. So suppose B is inside AB. Okay, then since we start with the point T0, then we can see that T0 beta, this interval in the segment, the closed segment, closed interval is a subset of AB. So T0 is contained in this interval AB, and beta is contained in AB by assumption. And so the assumption is that they are not equal, they are not the same. So the interval I is bigger, so I contains alpha beta, and this is a proper subset. So what does it mean? So we have the interval AB. We can't go away from this interval because our function is defined only for t from this interval. So J can't be greater than, larger than the interval AB. So it is inside AB, right? So alpha beta. But this is a maximal interval of this solution. So T0 is somewhere here. So this is T0. And by assumption, alpha, beta do not coincide with A and B or B. So alpha doesn't coincide with A, or beta doesn't coincide with B. And so they are different. Suppose beta is different from B. So we can see that this segment, this closed interval is inside I, right? Is inside the interval from A to B, right? You can see this. And now we will use the theorem about the compact set. So if we consider a compact set in D, then our solution must leave any compact set containing this initial point and contained in D, right? So let's use this theorem. I will draw a figure. I think the figure will help us. So this is t-axis, and we will consider the interval from A to B. Then this will be T0 and beta. And I'd like to consider compact set. So it will be, the compact set will be the direct product of the interval, so the closed interval from t0 to beta times, and I'd like to consider compact set, the direct product of two compact sets, and I want to consider a ball or a disk centered at the origin and of radius r. Let r be the radius. So, and it should be closed ball. So it will be the set such that less than r, less than or equal to r. So it must be closed. Is it clear? So the norm, the distance from x to 0. So in in R2, in plane, this means the following. So what does it mean? The closed ball. So we should put the center must be must coincide with the origin, right? And the radius of radius r, and it must be closed, so less than or equal to. So with the boundary is included, and all the points such that the distance from x, so this is the distance from the point to the origin, between the point and the origin.
It cannot be negative.
So can't be negative. So this is the norm. Norm is non-negative. So the set of points that are inside this disk. Okay, so I'd like to visualize this, and so I'd like to consider the disk. This is 3D graph, and so so this looks like an ellipse, right? So I'll try to draw the figure. So this is the direct product. Since we have the direct product, then the direct product of the segment and the ball, right? So the segment and the ball. The direct product will be this figure. This is the cylinder. Okay. Is it clear? So this is the center. This is B0R, and this is the same, right? And this is our compact set.
So this circle that you've drawn on the left there is basically it's a 3D circle, and it's a cylinder.
3D circle, right? That cylinder, right? So what is that direct product of the segment and the circle? So the segment multiplied directly by the circle, and this will give us the cylinder. So this is the cylinder, right? And we start with the point, so t0, and or maybe we should add something. It may be plus epsilon, maybe to start not with this point, but we should start from the point inside the cylinder, right? Let it be t0, and this is t0 plus epsilon. Let it be this, and this is this will be x0 bar.
Is epsilon negative? Because if it's going to the left.
Minus, right? Minus epsilon. So we start inside, from some point inside the cylinder, and our theorem guarantees that we will reach the boundary of this compact set, and go we will go out of this compact set of this cylinder as, so we leave the compact set. We leave K. K is the cylinder as as t approaches beta. So beta is so I think it right. So we must leave the cylinder as t approaches beta. And okay, the maximal interval of our solution is by assumption from alpha to beta, is this interval from alpha to beta. So we may leave this compact set only through the so lateral boundary, right? So not so we should go not through these two disks, but we should intersect the lateral boundary, right? This surface,
So
this boundary surface.
So we start living the cylinder from T0. This is when we start living.
Okay, so it is inside, right? So this point is inside the cylinder. But we should leave. We must leave this compact set as t approaches beta. Okay. For example, so I'd like to recall something. Let's I'd like to recall the example that was considered on the preceding lecture. X prime equals x squared, so was our differential equation, and it was solved, and the solution is obtained by 1 over c minus t, and for fixed c somewhere here, right, we have these solutions, and if we start from this point t0 and x0, so this trajectory, this solution should leave any compact set. For example, if we consider this compact set, we can see that the maximal interval is from negative infinity to c, right? And so this means that we must leave this compact set through the upper bound, right? Not the lateral bound, right? Or if we consider this compact set maybe equals c, so we must intersect this upper bound. And the same is true for this figure, right? So we can't intersect this because by assumption our solution is not defined for beta. So we must leave this compact through the so this boundary, so through this surface. I don't know how to call it. Do you know the surface of revolution? I think maybe, right? This one, right? But this is a contradiction. I'd like to obtain the contradiction with this inequality. So this fact contradicts this inequality because R is arbitrary. It can be chosen as large as we want. Right, so we can see that if R approaches infinity, we can see that this guarantees that x of t approaches infinity as t approaches beta, right? Because R can be chosen as large as we want. It can be chosen arbitrarily large, and we must. So what does it mean? So what is the norm of x of t? This is the distance from our point to the axis, right? This is the norm, and it can be done as large as we want, and so it approaches positive infinity, right? But this will contradict our inequality. stated in the hypothesis of our theorem, and I'd like to show the contradiction. So I need space, so I will use this space. So we know that x of t is a solution of initial value problem. If and only if x of t can be represented as x0 plus the integral from t0 to t f of s x of s ds. This was proved. It was a lemma. It was proved, I think, on the lecture number 2. So we will use this lemma. Then I want to obtain the estimate. Let's estimate the norm of this vector. By triangle inequality, it is less than or equal to the norm of x0 plus the integral from t0 to t, the norm of s x of s ds. But we're given that this norm doesn't exceed a of t times x times plus b of t, right? So we're given that this is bounded by, so the norm of, I will rewrite the norm of x0 plus the integral from t0 to t. We're given that it doesn't exceed a of t times the norm of x plus b of t ds.
How do you get the third inequality?
Which one?
The integration part.
This one. So we are given, so this is the hypothesis of our theorem. Look there. Part 3, we are given that f of tx doesn't exceed a of t times x and so on. So I just use this inequality, right? Okay, well, then we can rewrite it in the form norm of x plus the integral from t0 to t of b of t ds plus, okay, I'd like to estimate this, so I want to consider this. Not a of t, it is a of s. This is b of s. Okay, so we are given that a of s is a non-negative continuous function. Since it is non-negative and continuous, by extreme value theorem, it takes on its maximum value. So we can't find the supremum of a of s on the segment t0 beta. I will denote it by a. And so I will replace, so a of s, then we have a of s is less than or equal to L. L is a finite number because this is a segment, a is continuous, right? And so it doesn't exceed this x of s ds. Now b is a non-negative function, so we can replace t by beta, and we can write this plus the integral from t0 to beta b of not a, no, but s, b of s ds plus L times T0 T x of s ds. Okay, and if we denote this by the letter C, and this is L, we can see the following. We can see that the norm of x of t doesn't exceed C plus L times the integral from T0 to T ds. Okay, and now we can apply the Granola's lemma. So by Granola's lemma, so I will use this part. Then by Granola's lemma, if we have this inequality, if this inequality is satisfied, then x of t less than or equal to c times e to the power L times t minus t0. So t is arbitrary, but between t0 and beta, and so we can't. Or so we can use this estimation times c times e to the power L beta minus t0. And so this contradicts this fact. So we have obtained that the norm of x of t approaches positive infinity, but this inequality shows that the norm of x of t is bounded by this constant. So we come to the contradiction, and this completes our proof. So theorem is proved.
I have a question.
Right.
For this, the chart we're going to have, do we need to know?
Right, yeah.
What?
So you will need. So shall we have a break? So after this, we will move on to some new topic, maybe more, so less abstract, I think, less abstract and more computational. Right. So today we will consider the beginning of this large part of our study. It is called non-autonomous linear equations, and next lecture we will continue this topic. And today I will give the introduction to this topic. Is it so theoretical, right? Because it is, of course, theoretical because we have a lecture now.
No.
On the lecture?
No, I meant like, so in our last, how can I say, lectures, we were discussing more of a theoretical type of thing.
But on the seminar, we will solve problems, practical problems, not theoretical problems. But on the lecture, we always give definitions, prove theorems, so we can't avoid this. So because this is a lecture, right? So we will consider. I will use this part of the blackboard. The equation of the form x prime. So this is the vector function. The vector function equals the product of the matrix times x plus the vector b depending of t, where a of t is an n by n matrix, and b of t is a vector. And both a of t and b of t vary continuously with T. Okay, so example, I think. Right? So, for example, something like, let it be 2 by 2 matrix. In dimension 2, it will look like, so let it be x and y prime equals, so matrix A of t is a matrix. These are entries of our matrix. So A of t, B of t, C of t, and D of t are functions, 4 functions for 2 by 2 matrix, right? Multiplied by x and y plus some vector which will be, let it be f1 of t, f2 of t. Something like this. So this means this is the vector form or matrix form, and in the component form, in the coordinate form, we can rewrite this. So this means the matrix multiplication. So x prime is equal to A of t times x plus B of t times y plus f1 of t. So and the second equation will be y prime equals C of t times x plus B of t times y plus f2 of t. So A, B, C, D, so it is D. F1 and F2 are continuous functions. They are given continuous functions. And x and y are 2 unknown functions. And in what follows, we will consider the systems, linear systems of this form, and during the seminar we will try to solve them, right? And we will consider an example, maybe let it be. So this is the general example, but we will use the following example. X prime equals y, and y prime equals minus x. The example of this form. This is the example of, this is a particular case of this linear system, right? So this is a vector equation, but we are able to solve it now. It is not difficult to solve it. Let's try to solve. Maybe let's start with this. Let's try to solve this this linear system. How to do this? So solution is the following. Let's consider the first equation, for example, and differentiate one more time. So differentiate both parts. So let's take derivatives of both parts of this equation, right? We will get the following. X prime prime equals y prime. So this is the same as x double prime equals y prime. But now, from the second equation, we can see that y prime is negative x, so we can substitute minus x for y prime. Right? So, from the equation number 2, we can obtain that this is x2 primes equals negative x. We have obtained a single equation. It is a linear equation with constant coefficients, and it contains only one variable, and we know how to solve it because this was the topic of the preceding year, preceding semester, right? So we know how to solve this these equations. X2 primes plus x equals 0. Or we can use instead the technique of the Laplace transform. Okay, who knows how to solve? Okay, so we should consider the characteristic equation. So we start with the characteristic equation, and we need to obtain the roots of the characteristic equation. The characteristic equation is lambda squared plus 1 equals 0, and the roots are plus or minus I. Right? And this corresponds to the particular solutions cos x and sin x. And so the answer is x equals c1 cos t, sorry, plus c2 sin t. So this is the general solution of this equation. Okay, clear? Do you remember this? No? And you follow? Okay, well, so we will try to solve. So we will use the same algorithm in our seminar. So x is this. Then we want to know y, because the task was to solve this linear system. We have found x, but we don't know y. We need to find y. How to find y? Okay, so we can see from the first equation that y is equal to x prime. So to find y, we should differentiate. Y equals x prime from the first equation. So differentiate this, and we will get minus c1 sin t plus c2 cos t. This is y. And this is the complete answer. Or we will use the following. So we can rewrite this answer as in linear algebra. So using linear algebra, we can represent this solution as the linear combination of the vectors. So it is c1 times the vector cos t minus sin t plus c2 times sin t cos t. So you can see that a general solution is the linear combination of two particular solutions with some arbitrary constants c1 and c2. Right? So during the lecture, I'd like to generalize this result. Right? So we will try to prove that any general solution can be represented as a linear combination of particular solutions, not only for, so it looks like the homogeneous linear system in the course of linear algebra, but this is also true in the course of differential equations. Also, we can find, so in dimension 2, we can find two linearly independent particular solutions to this differential system, system of differential equations, and represent the general solution as the linear combination of two particular solutions. So this will be the topic of our lecture. So let's return to our lecture. Right, so this is called a linear system. This is the linear system. A of t and b of t are continuous functions. And this is called the linear system. It is linear in x because x is not raised in some power. We don't take any function of x, so x raised in the first power. So this system is called linear in x. It is a linear system. It is called or just the linear equation. So a linear system or a linear equation if we mean the vector. So if by function we mean a vector function. So or a linear equation.
Use this way to solve that question right there.
So this is that terminology. So this is just the introduction of some terminology, and we will not use this. So we will use theorems, of course, not definitions. Linear equation. I will call this a linear equation, right? Okay, let's discuss first. Let's discuss the Picard-Lindelof theorem. Does it work here? Picard-Lindelof theorem. Does it work for our equation? So to apply the Picard-Lindelof theorem, we must check that the function f of t, vector function, defined as the a of t times not must be continuous and locally Lipschitz in X. Is it continuous and locally Lipschitz in S? In X, is it continuous? Yes, this function is continuous because a of t and b of t are both continuous functions. It is continuous. And is it locally Lipschitz in X? Yes, of course, because the partial derivatives with respect to X, not with respect to t. So a of t and b of t may not be differentiable functions of t. They are only continuous functions. But they need not be differentiable. So we need not this fact. Because the function should be locally Lipschitz in X. But we can find the partial derivatives of f with respect to X because this is the linear function, and it is, of course, differentiable with respect to X. And if the function is of class C1, and it is, if the function of class C1, so it has continuous partial derivatives, then it is locally Lipschitz. So it is locally Lipschitz. And we can apply the Picard-Lindelof theorem to this linear equation. By the Picard-Lindelof theorem, the solution passing through the point t0, x0, so the initial value problem has a, so let's consider, I'll write the initial value problem. Has a unique solution locally. But what about the maximal interval? The maximal interval. Okay, so theorem 1 says that the maximal interval of this solution is the entire real line. So it can be stated as all solutions have maximal interval R. The entire real line. Let's prove this. We will use the preceding theorem about global existence. On global existence. Proved earlier today. So to apply this theorem, we should try to write the inequality. F of t of x is this function. Okay, it's this. By triangle inequality, it is less than the norm of a of t times the norm of x plus the norm of b of t. And so the hypotheses of the theorem on global existence are satisfied because, so with A of t, which is equal to the norm of the matrix A of t, and we can use the norm, so the square root of the sum of squares of the entries, for example, right? And this is B of t. These functions are both non-negative because they are equal to norms, right? They are non-negative and continuous. And so we can apply theorem on global existence. It states that any solution can be extended to an interval I is fixed, but so this inequality is true for t, for any t and any x. It is true in the domain which is equal to r times Rn, because it is true for any t real and any x. So we can apply theorem of global existence with I equals R, the entire real line. And so this proves that the solution exists, have maximal interval R, the entire real line. Theorem is proved. So just to apply the preceding theorem, very easy.
The solution that just satisfies the initial values, right?
Initial value problem. Yeah. This is the abbreviation for initial value problem, right?
And that means it's a solution which satisfies the initial value.
The initial value, right. So we take any t0, any x0, consider the solution. Locally, it exists and is unique by Picard-Lindelof theorem, but by this inequality, any solution can be extended to the entire real line. So any solution is defined on the entire for any t, right? It can be extended for any t. Well, so that is why we need that preceding theorem, right? So I turned back to the preceding lecture and proved the theorem because it is important, right? Okay. So a solution, I will give the following definition. A solution x of t of the initial value problem is called global. Global, if it is defined for any t. And so corollary from our theorem. So from this theorem follows that any solution of a linear differential equation is global. So this definition is general. A solution of any initial value problem, not necessarily linear, right? So this is the definition of global solution. And corollary says that any solution of a linear equation is global. Well, now we will consider a homogeneous differential equation. So for today, so up to the end of this lecture, we will consider homogeneous linear differential equations. Homogeneous means that this constant so this vector function is identical 0, right? Homogeneous linear differential equation. I will use this part. We will consider homogeneous linear differential equation of the form x prime of x prime equals a of t times x. And this is the initial value problem. So sometimes we need only the equation for, so we will be looking for general solution of this equation, or sometimes we may consider an initial value problem, right? So this is an initial value problem, and in what follows, so up to the end of this lecture, we will consider homogeneous linear differential equations, and we need to know some facts about it, and we want to prove first that the set of all solutions of a homogeneous linear differential equations form a vector space. And we will start with the linearity principle. This will be theorem number 2, linearity principle. It tells us that if x1 of t dot xn, x may be k of t are solutions of our differential equation, then their linear combination is also a solution. Okay, the linear combination. Look at this example. Okay, look at this linear combination, right? So we can see that these are two particular solutions, and this is their linear combination, and their linear combination is also a solution. And this theorem is a general theorem, and it states this fact in the most general case, right? For any matrix A, maybe depending on T. So the only requirement is that this matrix should be continuous, should vary continuously with T. Right, so we will prove it. Okay, so let's take the vectors x1, xn, depending on T, of course. Then take their linear combination and try to find their derivative. Let's differentiate this. By the property of the derivative, the linear combination, so the derivative of the linear combination is equal to linear combination of derivatives. I think it's clear. Then we know that they are solutions. Okay, they are solutions. Since these functions are solutions, then we know that each derivative is equal to a of t times x. k times a of t times xk. We just substitute this equation. We know that x1 and so on xn are solutions of this equation, and I have substituted this into our equation. And so we know the property of the matrix product, and we can see that we can rewrite this as the product of the matrix A of t times C1 x1 plus dot 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 plus ck xk. And from the last formula, we can see that this linear combination also satisfies the original equation, original differential equation. So theorem is proved. The linearity principle is proved. Well, now I want to prove another theorem. I'd like to prove the following theorem. So theorem number 3, the set of all solutions of this homogeneous linear differential equation is a vector space of dimension n. So the set of all solutions is a vector space of dimension n. The set of all solutions is a vector space of dimension n. Let's prove it. So we know that the linear combination of any k solutions is also a solution. But now we want to show that this space is n-dimensional. So we need to find the basis. So find the basis in the solution space. How to do this? Okay, fix any t0 Okay, so initial value, the set of all solutions. Right. Fix any t0 and take. Okay, right. Any t0. Let it be this. Okay, consider the standard basis. The standard basis consisting of vectors e1 and so on, en. Okay, do you remember what is it? The standard basis. The standard basis. So this means that e1 is equal to 1, 0, dot, 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 0, right? e2 is 0, 1, 0. en is 0, 0, 0, 1. Okay, and we will consider n initial value problems. Consider, so an initial value problem. so the following one, x of t0 equals ei. Okay, so there will be n initial value problems. I runs from 1 to n. So n initial value problems. And for each initial value problem, we will find a particular solution. And we will find, we'll obtain n particular solutions. x1 of t dot xn of t. So is it clear? So each of these functions is a particular solution of the corresponding initial value problem. So x1 corresponds to the initial value problem, x of t0 equals e1. Right? So we start with this point, linearity principle, yes, but we must show that the basis is finite. We should show that I want to show that these functions form a basis. And the basis consists of n function. So it is important that the dimension of the space is n. It is finite dimensional and dimension is n, and so to show this we need the basis, right? Of course we will use the linearity principle. Linearity principle shows that this is a vector space, but this theorem states that it is n-dimensional. It is important, of course. It may be infinitely dimensional. Sometimes some vector spaces are infinite dimensional, right? So n particular solutions. Okay, and I'd like to show that any solution is a linear combination of these solutions. By linearity principle, we know that any linear combination is a solution, but I'd like to show that any solution, so to prove that this is a basis, so I want to prove that this is a basis. Now, to prove that this is a basis, I'd like to show that any solution can be represented as their linear combination first. And next, I will show that they are linearly independent. Linearly independent. Okay, well, so how to show that any solution can be represented as this linear combination? So any solution of the initial value problem, take any solution. With x of t0 equals x0. So we consider an arbitrary point, right? An arbitrary vector. And this initial value problem will give us a solution, x of t. And I want to show how to represent this solution as a linear combination of the basis. Okay, so to do this, I will start with x0. x0 is any vector. It doesn't depend on t. It is a fixed vector, and it can be represented as a linear combination of these basis vectors. Right? So it is c1 e1 plus c2 e2 plus cn en. Since e1, e2, and so on, en form a basis in Rn. So there exist. This is the part of the proof, yeah. So I'd like to show that any solution can be represented as a linear combination of basis vectors. Well, and since by the Picard-Lindelof theorem, x of t is unique, then it exists and unique, then I claim that x of t is equal to C1 x1 of t plus C2 xt2 of t plus dot 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 plus Cn times xn of t. Okay, so how to prove that x of t then is this linear combination? First, we know that it satisfies the solution by the linearity principle. This satisfies the equation, right, the linear equation by the preceding theorem, and it satisfies the initial value problem, right, the initial conditions, because we have found C1, C2, and so on, Cn, so that x0 is this linear combination. So we have proved that x of t then this linear combination, right? And the second step, I wanted to show that this is a basis. This is a basis, but to show that some set of vectors form a basis, we need to show that any vector can be represented as their linear combination first, and that they are linearly independent. Okay, I want to show x1 of t, xn of t are linearly independent. So linearly independent vectors, but they depend on t, right? I'd like to recall that this means that the equation C1 times x1 of t plus dot 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 plus Cn xn of t. So this equation, which must be satisfied for any t, is satisfied only for 0 values of c, right? This is satisfied if and only if all the constants are 0, are identical 0. This means that x1 and so on xn are linearly independent, right? And this is for any t. So take t equals t0. Then we know that x1 of t0 is E1, right? So we know that xi of t0 equals EI by this initial value problem, right? By this condition. So for t equals t0, this equation is reduced to the equation C1 times E1 plus C2 E2 plus dot 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 plus Cn En equals 0. But this is satisfied only for C1 that are identical 0, because E1, E2, and so on, En are basis vectors in Rn.
Well, what about for t which is not equal to t0?
What about what? Could you repeat?
For t which is not equal to t0.
So, okay. This equation, the vectors depending on t are linearly independent. It's better to say what does it mean that they are linearly dependent. So they are linearly dependent if there is some numbers C1 and so on Cn which are not identical 0, such that this linear combination is equal to the 0 vector for any t. So they are linearly independent if there exists t such that it is not satisfied. So there exists t, not for any t. For example, just a moment. For example, the vectors 1 and t, and let's consider these two vectors sine t. Are they linearly dependent or independent? Independent, yes, but but we can see that for t equals 0, they are the same, right? It depends on t, independence t, and this is also dependent on t. Okay, at one point, one value of the parameter, they are the same, but for other t, they are not the same, and they are linearly independent. And in general, this means that these two vectors are linearly independent. They may be dependent in for several values of t, not for all values for t, right? So this is the case, but next time, so on the next lecture, we will prove that if these are solutions to the linear differential equation, there are only two alternatives. They are so these vectors are linearly dependent for any t or linearly independent for any t. So it can't be the situation. The situation like this is impossible for solutions of a differential equation, right? So it is impossible for two vectors to be linearly dependent at one point and linearly independent for other points.